Hello everybody, I am Mika Seppälä. In this video I discuss Taylor series of basic functions, namely the exponential function, the sine function, the cosine function, and the function which is of the form 1 plus x to the power p, where p is a number, maybe a positive or negative, doesn't need to be an integer. If a function f is infinitely many times differentiable at x equals a, we may form its Taylor series, which is summation k from 0 to the infinity, k's derivative of f at a divided by k factorial times x minus a to the power k. This is a power series in terms of powers of x minus a. In this notation, the zeroth derivative of a function means the function itself, and 0 factorial is defined to be just 1. The special case a equals 0 is also called MACLAURIN series. So the MACLAURIN series of a function f is its Taylor series at x equals 0. So MACLAURIN series is a special kind of a Taylor series. Partial sums of the Taylor series, that is, polynomials which are of the form summation k from 0 to n, k's derivative of f at a divided by k factorial times x minus a to the power k, are called Taylor polynomials of the function f at x equals a. Taylor's theorem is a sophisticated generalization of the mean value theorem. In Taylor's theorem, we assume that the function f is n plus 1 times differentiable. If that is the case, we may form degree n Taylor polynomial of the function f at any point. The degree n Taylor polynomial of f at x equals a is summation k from 0 to n, k's derivative of f at a divided by k factorial times x minus a to the power k. Taylor's theorem states that there is a number cx between a and x, such that the error that we make when we approximate the values of the function with those of its Taylor polynomial of degree n at x equals a is the n plus first derivative of f at this point cx divided by n plus 1 factorial times x minus a to the power n plus 1. This point cx depends on x, it also depends on n. The only thing we know is that the point cx is between a and x. This is a very powerful result, and it allows us to show that Taylor series for many basic functions converge, and the sums of these series are those basic functions themselves. This is what makes Taylor series so powerful. The Taylor series at x equals 0 for the function f of x equals e to the power x can be easily formed, because the exponential function has a property that its derivative is just the exponential function itself, and also all other higher derivatives are just the exponential function itself. And this means that the value of the function and that of all of its derivatives at x equals 0 is just 1. Therefore, the Taylor series at x equals 0 for the exponential function e to the power x, that is the MACLAURIN series for the function, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so forth. That is summation k from 0 to the infinity, x to the power k divided by k factorial. It is easy to see that the radius of convergence of this power series is the infinity. It means that this power series converges for all values of x, and hence defines a function which is infinitely many times differentiable. We wish to show that this function is the exponential function itself. In order to do that, we have to estimate the error that we make when we approximate the exponential function with degree n Taylor polynomials at x equals 0, and we use Taylor's theorem to this end. By Taylor's theorem, there is a number cx between 0 and x, such that e to the power x minus summation k from 0 to n x to the power k divided by k factorial equals e to the power cx divided by n plus 1 factorial times x to the power n plus 1. We wish to show that this error approaches 0 as n grows. In order to do that, we need to take a closer look at the error term. In order to estimate the error, consider the quantities an defined by setting an equals e to the power absolute value of x divided by n plus 1 factorial times the absolute value of x to the power n plus 1. By this definition, an plus 1 equals e to the power absolute value of x divided by n plus 1 factorial, that is n plus 2 factorial, times the absolute value of x to the power n plus 1, that is the absolute value of x to the power n plus 2. This expression for an plus 1 can be rewritten as the absolute value of x divided by n plus 2 times e to the power the absolute value of x divided by n plus 1 factorial times the absolute value of x to the power n plus 1. Here we have simply used the fact that n plus 2 times n plus 1 factorial is n plus 2 factorial, and that the absolute value of x times the absolute value of x to the power n plus 1 is the absolute value of x to the power n plus 2. This rewriting has the advantage that now we see that n plus 1 is the absolute value of x divided by n plus 2 times an. And this means that, first of all these numbers an are positive, and that if n is larger than 2 times the absolute value of x, then the absolute value of x divided by n plus 2 is less than 1/2. Therefore, if n is larger than 2 times the absolute value of x, 0 is less than an plus 1 is less than 1/2 times an. And this double inequality means that as n grows towards the infinity, the limit of these numbers an must be 0. Now recall that by Taylor's theorem there is a number cx between 0 and x, such that the absolute value of e to the x minus summation k from 0 to n x to the power k divided by k factorial equals e to the power cx divided by n plus 1 factorial times the absolute value of x to the power n plus 1. Now, we do not know which point cx is. It depends on x and it also depends on n, but it always lies between 0 and x. Therefore, the absolute value of cx is at most the absolute value of x. And this means that e to the power cx is less than or equal to the e to the power the absolute value of x. And therefore, this quantity is bounded by above by this expression e to the power absolute value of x divided by n plus 1 factorial times the absolute value of x to the power n plus 1. And this is the quantity an that we just considered a moment ago. And we know that the limit of these quantities an is 0 as n grows towards the infinity, and this means that the limit as n goes to the infinity of e to the power x minus summation k from 0 to n x to the power k divided by k factorial is 0. And this means that the MACLAURIN series for the exponential function e to the x, that is the Taylor series at the origin, which converges for all x, gives as its sum the exponential function. That is that for all x we have e to the x equals the sum of the series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so forth. That is summation k from 0 to the infinity x to the power k divided by k factorial. Let us next consider the sine function. To form the Taylor series of the sine function at the origin, that is the MACLAURIN series, we have to compute values of derivatives of the sine function at the origin. First of all, the sine function itself takes the value 0 when x equals 0. Its derivative is cosine, and the value of cosine at the origin is 1. The derivative of cosine is negative of sine. Its value at the origin is 0. The derivative of negative of sine is negative of cosine. Its value at the origin is negative 1. And finally, the derivative of negative of cosine is sine, whose value at the origin is 0. Now, by differentiating 4 times, starting with the sine function, we got back to the sine function. This means that the pattern repeats and values of the function and its derivatives follow this pattern 0, 1, 0, negative 1, 0, 1, 0, and so forth. And this means that the Maclaurin series for the sine function, that is the Taylor series at the origin, is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus and so forth. That is summation k from 0 to the infinity, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. We will use Taylor's theorem to estimate the difference between the value of the sine function at x and that of its Taylor polynomial of degree 2 times n plus 1 at x. We consider Taylor polynomials at the origin. This difference is sine of x minus summation k from 0 to n, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. By Taylor's theorem, there is a number cx, which is between 0 and x, which depends on x and depends on n, such that the difference of sine of x and that of its Taylor polynomial of degree 2 times n plus 1 is of absolute value the same as the absolute value of 2 times n plus second derivative of sine evaluated at c of x divided by 2 times n plus 2 factorial times the absolute value of x to the power 2 times n plus 2. Now in this estimate we still have to deal with this somewhat complicated expression on the right hand side, and we observe that depending on n, the 2 times n plus second derivative of sine is either plus or minus sine or plus or minus cosine. Its value at the point c of x is therefore either plus or minus sine at c of x or plus or minus cosine at c of x. In all cases, this value is of absolute value at most 1. Hence, by Taylor's theorem, the absolute value of the difference sine of x minus summation k from 0 to n, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial is at most the absolute value of x to the power 2 times n plus 2 divided by 2 times n plus 2 factorial. These upper bounds tend to 0 as n grows. In order to see why that happens, let an denote the quantity the absolute value of x to the power n plus 1 divided by n plus 1 factorial. Then an plus 1 is the absolute value of x to the power n plus 2 divided by n plus 2 factorial. And that can be rewritten as the absolute value of x divided by n plus 2 times the absolute value of x to the power n plus 1 divided by n plus 1 factorial. This follows since n plus 2 times n plus 1 factorial is simply n plus 2 factorial. Therefore, an plus 1 is the absolute value of x divided by n plus 2 times an. And this is less than an divided by 2 if n is larger than 2 times the absolute value of x. But now we are interested in the situation where n tends to the infinity. Then it follows from this estimate that the limit of these quantities an as n tends to the infinity is 0. Since the error terms are bounded by numbers which approach 0 as n grows, we conclude that the sum of the Maclaurin series for the sine function is the sine function itself for all x. That is, that the Maclaurin series both converges and that its sum is sine of x for all x. So we conclude that sine of x equals x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus and so forth, that is sin of x equals summation k from 0 to the infinity, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. This convergence can be pictured graphically in the following way. Consider the sine function and its Taylor polynomials Pn, which are defined by setting summation k from 0 to n, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. In this picture, we see the graph of the sine function, which is the black curve, and that of the Taylor polynomial corresponding to the value n equals 1. This is the Taylor polynomial of degree 3. Its graph is the blue curve shown here. And near the origin, this Taylor polynomial approximates the sine function pretty well, but the approximation fails to work when we get further away from the origin. In order to get approximations that work further away from the origin, we need to take higher degree Taylor polynomials. This green curve here now corresponds to a Taylor polynomial obtained by setting n equals 5, that is a Taylor polynomial of degree 11. And clearly it approximates sine function better further away from the origin, but of course after some point it fails to approximate the sine function. To get an approximation that works even further away, we take a higher degree Taylor polynomial. This red curve corresponds to n equals 10, that is Taylor polynomial of degree 21 for the sine function, and it approximates sine function pretty well already over a large interval. To find the Taylor series for the cosine function at x equals 0, that is the MACLAURIN series for the cosine function, start with the MACLAURIN series for the sine function. Sin of x is now summation k from 0 to the infinity, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. And this series converges for all x. Now we know that the derivative of sine is cosine. Therefore, cosine of x is the derivative of this power series summation k from 0 to the infinity, negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. And the derivative of a power series can be computed by differentiating the power series term by term. Therefore, we conclude that cosine of x equals summation k from 0 to the infinity, derivative with respect to x of negative 1 to the power k, x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial. The derivative of x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial is 2 times k plus 1 times x to the power 2 times k, and this divided by 2 times k plus 1 factorial. But here 2 times k plus 1 cancels out, and we observe that this derivative is simply negative 1 to the power k, x to the power 2 times k divided by 2 times k factorial. Therefore, we conclude that cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus and so forth. That is summation k from 0 to the infinity, negative 1 to the power k, x to the power 2 times k divided by 2 times k factorial. And this picture here shows the graph of the cosine function and those of its degree 4, 10, and 20 Taylor polynomials. The higher degree Taylor polynomial you take, the better approximation for the cosine function one gets. The MACLAURIN series for the function f of x equals 1 plus x to the power p is called the binomial series. Here the parameter p may take any real value. It is not restricted to integers. If p is a positive integer, then 1 plus x to the power p is simply a polynomial of degree p, and its MACLAURIN series is that polynomial itself. If p is not a positive integer, then this is an infinite series. And in order to form this series, we have to evaluate the function f and its derivatives at the origin. The function f is 1 plus x to the power p. Its value at the origin is just 1 to the power p, which is p. Its first derivative is p times 1 plus x to the power p minus 1. The value of the first derivative at the origin is p. The second derivative is p minus 1 times p times 1 plus x to the power p minus 2, and the value of the second derivative at the origin is p minus 1 times p. The third derivative, which is not shown here, is p minus 2 times p minus 1 times p times 1 plus x to the power p minus 3. Its value at the origin is p minus 2 times p minus 1 times p, and so on. Therefore, we conclude that the Maclaurin series for the function 1 plus x to the power p equals 1 plus p times x plus p times p minus 1 divided by 2 factorial times x squared plus p times p minus 1 times p minus 2 divided by 3 factorial times x cubed plus and so forth. And one can show that this series converges whenever the absolute value of x is strictly less than 1 and that it represents the function 1 plus x to the power p on the interval from -1 to 1. For example, square root of 1 plus x is 1 plus 1 half times x minus 1 divided by 4 times 2 factorial x squared plus 3 divided by 8 times 3 factorial x cubed minus and so forth. And this series expansion for square root 1 plus x is valid for x between -1 and 1. We have obtained the following basic Maclaurin series. For the exponential function e to the x, we have e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so forth. That is e to the x equals summation k from 0 to the infinity x to the power k divided by k factorial. Sine of x equals summation k from 0 to the infinity -1 to the power k x to the power 2 times k plus 1 divided by 2 times k plus 1 factorial, and cosine of x equals summation k from 0 to the infinity -1 to the power k x to the power 2 times k divided by 2 times k factorial, and finally the binomial series is that 1 plus x to the power p equals 1 plus p times x plus p times p minus 1 divided by 2 factorial times x squared plus and so forth. The binomial series converges if the absolute value of x is less than 1. All the other basic Maclaurin series converge for all values of x and represent the function in question.